Tonight, our topic is the universe. It's kind of a big topic, but we're going to break it down into pieces. And we're thinking about how in ancient times, in the times of kings and queens and princes, when the prince came of age, he was supposed to ride the boundaries of the kingdom and know what those boundaries were, know what his kingdom was. And so what we're going to do is we're going to ride the boundaries of the kingdom of the universe, which is our inheritance. And we're going to do it in terms of size, because just as a timeline gives you a way of organizing history, a size line gives you a way of organizing the natural sciences. You know, we're used to saying, really, that size is not important, because it doesn't matter whether you're tall or short, you're still a person. But when we're talking about the physical sciences, the natural sciences, biology, chemistry, physics, meteorology, geology, and astronomy, size really does make a difference. So we're going to be talking about size. And before I begin, I just want to say one thing about number to make it clear to you what some of the things are that we're going to be saying. I want you to understand the concept of a billion. And I want you to understand it in a particular way. If you took 1,000 cranberries, or something like that, and made a line out of them, and then made a whole entire floor that was 1,000 cranberries this way and 1,000 that way, or 1,000 centimeters, and then if you went up, then you would have a billion cranberries. You'd have 1,000 times 1,000 times 1,000, and that's just about what would fit into a barn. So if you take one cranberry or blueberry and roll it out of a barn, that's a billionth of the size of a barn. So I want you to keep that concept of the billion in your mind. So let me take a minute to talk about the early universe. Because of the immense spaces that we have between galaxies and groups of galaxies, the question has arisen, what was the really early universe like? And it now seems as if it was like, of course, at the beginning, just all the matter very tightly clumped together, but that when it expanded, it didn't just expand evenly, but it expanded as if somebody were blowing bubbles in the liquid of the universe, so that you ended up, not ended up, but in the very early part of the universe, it was as if all of the matter in the universe was a foam of bubbles sitting in God's hand or in the universe. And that foam rapidly became bigger, just the way it does if you blow a foam of bubbles, of soap bubbles in your hand. Now, when you pop a soap bubble in front of your face, you can feel the droplets against your face. Because you feel them against your face, we know that film doesn't go right away to breaking into molecules. You wouldn't feel molecules. What happens is that the film tears up, and those little bits of torn film pull themselves together, and then that's what hits your face. So what we're imagining is that in the early universe, this bubble foam became bigger and bigger, and suddenly, as it were, popped. And the droplets didn't fall down, because there's no down at this point in the universe, but it continued to expand outwards quite suddenly. That's what happens when a bubble pops. But the shape of the bubble remained. That is to say, all of the little bits of bubble film pulled together into galaxies. And the empty parts of the bubble remained empty, so that we have within the universe, even now, vast areas that have no galaxies in them at all. And then we have other areas where it's like a wall of galaxies. So we're going to begin with the concept of the entire universe. And the whole universe is about 10 to the 27th meters in diameter. That means 10 times 10 times 10 times 10 times 10 times 10 times 10, 27 of those meters in its going all the way across. And this is a representation of that universe in God's hands. And a billionth of the entire universe would be just one of these sections where you have galaxies. And the interesting thing is that the galaxies, instead of being arranged like salt on your egg, just randomly sprinkled around. In the 1980s, it was discovered that the galaxies were arranged in walls and clumps and little pieces that looked as if the universe maybe had started as a handful of bubbles. After that is you have arrangements of galaxies, and in between those arrangements of galaxies, huge open spaces, 500 million light years across, with nothing in them. 200 million, 500 million. And that's what we're looking at here. We're looking at these vast empty spaces and these strings not of stars, but of whole galaxies. So now let's take a billionth of that. And when we take a billionth of that, what we have is just one galaxy. This particular galaxy this is a picture of the Sunflower Galaxy, which is somewhat like the Milky Way. The main galaxies are about 10 to the 21st meters across. The Milky Way, the Sunflower Galaxy, they're all different. There's a Sombrero Galaxy, which has such a long, thin area, and then a big round area as if it were a sombrero. And so they all look different. You never come to a part of the universe where everything's just the same as everything else. About a billionth of the size of the galaxy is the size of some of the large structures in the galaxy. What I have here is I have the constellation Orion. Orion is one of the most delightful constellations to see, and many of the stars that we see in the sky are about 100 light years away, or several hundred light years away. We don't see things that are too much farther away than that because they're just not bright enough. One of the things that's interesting in Orion that we don't see is there's just a whirling electrical piece of activity that's 100 light years long. And what is it doing? It's acting like a motor with no machine, no car for it to drive, nothing. So again, always interesting things. When we get down to a thousandth of that, then we come down to things like the Cat's Eye Nebula. Now, we need to talk a little bit about the lives of stars. A small star burns hydrogen into helium over a very long period of time. There are some stars that are as old as the universe. They're 13 billion years old. They have another 13 billion years before they quit because they're not very big and they don't burn very fast. Larger stars will burn hydrogen into helium, and then they'll kind of cool off for a while, and as they cool off, they shrink down like other things that get cool, and after they shrink down for a while, they start compressing again, and they compress the helium into carbon. And so that's the next thing that happens. There's this heating up of helium being fused into carbon, and then heat is produced, and it starts to grow again, and it starts to become big. And after all of the helium has burned into carbon, then it cools off, and it collapses down, and it gets smaller. And then it can go through another round and go from carbon to silicon. Heat up, cool down. But here's the interesting thing. When it heats up, the outside of the star, which is just gas, goes out far, far, far away from the star. And when it cools off and everything collapses down, some of this gas out here doesn't fall all the way back down. It just sits out there saying, well, you know, I'm pretty light, I don't have to fall back down. So the star gets down and it becomes small again. And out here there's a ring of gas, which isn't very conspicuous, except if you're looking at it from the side, then it looks as if there's a ring around the star. It's actually an entire bubble around the star, but it's most visible around the ring. And that's what you have here with the Cat's Eye Nebula. You have what's called a planetary nebula. The star has done a big blow up and it's cooled back down again. So that's what happens with big stars. Then we come down to the size of our own solar system. Now, there's different ways of counting how much is part of our solar system, but if we take our solar system out just somewhere between Jupiter and Saturn, then we're talking about 600 million
Miles.
across, or 600
Million miles.
out from the sun.
1,200 million miles across.
That's the next size range, and there are some stars that are pretty close to this size range. There's one called Mu Cephei. It's in the constellation Cepheus. It's called the Garnet Star, and the Garnet Star is very red. And it's red because it's very big and it's a little bit cooled off, but it's also one of those stars that already has burned hydrogen into helium, helium into carbon, carbon into silicon, and silicon into iron. And that's as far as stars can go that way. To get the higher elements on the periodic table, you can't do that inside of a star because you can't do it by compression. The problem is that at that point when you compress, instead of producing heat, the new element pulls in heat, and that stops the reaction. So you never go very much farther. But then, here's what happens in a very big star, then you have an explosion. Just a minute. The star cools down, and it cools enough that it comes to the point where all of a sudden, almost all of this gas out here collapses down. And when I say all of a sudden, I don't mean all of a sudden over a mere 1,000 years. I mean seconds. All of this stuff collapses down, hits the center of the star, and bounces back out again. And that intensity of explosion is so great that all of the other elements in the periodic table are made by that explosion. It's called a supernova. So supernovas are mostly bigger than the planetary nebula. Of course, in the beginning, they're tiny, they're only the size of this little star. But they're important because a star which is about to become a supernova can be as big as our whole solar system. If we put Mu Cephei right on top of the sun, its atmosphere, its redness, would go all the way out as far as Saturn. Amazing. So now the next thing, the next thing is a billionth of the size of the whole solar system. So a billionth of the size of the solar system, now we're finally down to the size of our sun. And stars are very particular in their sizes. What's interesting about it is because the thing that makes a star burn is its own gravity, anything that has enough gravity is going to burn. If you had cotton candy the size of the sun, that cotton candy would burn. Whatever it is, there's a certain size where the weight is sufficient to crush and cause burning and cause atomic fusion. Actually, our planet Jupiter, which has about 1/10 of the diameter of the sun, is almost big enough to burn. About 10 Jupiters would begin to burn and be a small star. So just to understand, that's why stars have a particular size. You don't have a star the size of your elbow. The stars are not something that's up there and then God lights them. They light because of their size. So let's talk about what would be a billionth of the size of the sun. And it's interesting here because 1,000th of the size of the sun, meaning 1/10 of the diameter, and therefore 1,000th of the size, would be Jupiter. And 100th of the diameter, 1,000,000th of the size, would be Earth. But 1,000,000,000th of the size of the sun, 1,000th of the diameter, would be the size of Ceres. Ceres is a very interesting asteroid because it's the only asteroid that's big enough that it's been able to pull itself into a circle. Most of the asteroids are sort of potato-shaped, bean-shaped. But this one is round. It looks a lot like the moon. You probably think the moon is what I'm showing you here. It's kind of like if you took an ice cream scoop and scooped California out of the globe. Then you would have something the size of this asteroid. And there are lots of asteroids. They're all in this size range. It's about 1,000 kilometers, about 600 miles in diameter. And so now if we take 1,000th of that, we have the size of a small volcano. Volcanoes can only be so big because they're loose, and the stuff that comes out of the volcano falls back down again, and gravity starts pulling the whole thing down and ripping it apart. So the Arima volcano in Costa Rica is about 1 kilometer high. That's just the way it is. And in fact, all of our mountains, because of these angles,
Repose.
are in this neighborhood. We know that Mount Everest is 5 miles high, but the truth is, all the stuff around Mount Everest is high. If you would go from sort of the baseline of mountains around it, it's nothing like 5 miles. So anyway, a kilometer. 1,000th of a kilometer is 1 meter. So now when we ask ourselves, what typical thing in the universe that's important to us is 1 meter? The answer is we are. We're a little bit more than a meter. Our children are a little bit less at different periods in their life. But 1 meter is the size of ourselves. And it's the size of all of the domestic animals. Not that they're all 1 meter, but they're 1 meter or 2 meters. A few of them are 3 meters. You have to be talking about things like brontosaurus or whales to get something that's not in this size range. This is the size range of mammals. And it's interesting, mammals produce heat on the inside by their metabolism, and they get rid of heat on their surface. So when you go down, down, down in size to the size of bugs and beetles, you have only a tiny little bit of inside, and you have a huge surface comparatively. And they can't keep themselves warm. So they make their blood out of antifreeze, and they curl up in the winter in some kind of way. But the mammals are this size and maybe a little bit smaller. And that's the next realm of interest. This is a picture of a flea. A flea is one of these little creatures that can't keep itself warm except by staying in a warm place or turning its blood all to antifreeze during the winter. And 1 billion times smaller than the flea is the chloroplast. If you look inside a cell is about 10 to the minus 5th, and a chloroplast is 10 to the minus 6th. If you look inside of a cell of a green plant, you'll see these little tiny like ships going around the edge of the cell. And these are the chloroplasts, which is where the cell has all the little machinery for taking sunlight and making sugars. Tiny, tiny, tiny little thing, but it's not the smallest thing in the world. The next thing down that we need to talk about is 10 to the minus 9th. And 10 to the minus 9th is basically the size of our molecules, large molecules. The very smallest ones aren't even in this place, but 10 to the minus 9th, this is one of the biggest molecules. It's called a ribosome. If you read in biology about the partitions between different parts of the cells, one of them is called the rough endoplasmic reticulum. And it's rough because it has little dots on it, and those little dots are ribosomes. And the ribosome is the protein factory of the cell, so that's where everything is done to make the different kinds of proteins that are needed for building all different parts of the body. So now, 1 billionth of the size of the ribosome, 1 billionth of the size of a ribosome is difficult. Here's why. There's really no thing that's that size. What you have is 1/10 of the diameter, and therefore 1,000th of the size, is the size of the atoms. And all the atoms are in basically the same size classification, 10 to the minus 10th meters. 10 to the minus 11th, there really isn't anything in that size range. 10 to the minus 12th is, okay, if you took a carbon atom, and if you've studied atoms, you know that there's a proton in the middle and there are electrons around the outside. And the electrons that are on the farthest part of the outside have these huge orbits, and the electrons farther in have smaller orbits. Well, if you could take the outer electrons off a carbon atom and just look at that lower level, that would be about the size. the electron orbits inside there would be about 10 to the minus 12. But the funny thing about an electron is that we don't really have a size for it. It's not 10 to the minus 15, 16, 17, 18, 19, 20. We can't see any farther. It seems to be infinitesimal, but we're putting it here because the electron orbits in the lower parts of the carbon atom would be in this size range. And the last thing that we come to is the proton. Now, the proton is the smallest object in the universe for which we have a size and a weight. And it's a definite size and a definite weight. It's actually about 3 times 10 to the minus 16th. So we're putting it here. Now, when we look at this whole arrangement, it's been pretty quick, but look at what happens. Up here, at the largest size, we're talking about cosmology. What is the universe? What does the whole of the universe look like? What size does it have? Does it have a size? We've concluded in the last 50 years that it does have a size. Then the next part that we see down here is what we would study in astronomy, the stars and the galaxies. And the interesting thing here is we had a certain point, if you look up in the sky, all the stars are, at first, they kind of all look similar, not very bright, not very big, pin size. But when you actually can look at the stars, they're all different. They're burning different things. They're all on different schedules. They're different closeness to each other. The galaxies are all different. The planetary nebula are all different. We're asking ourselves, how many of these stars have planets like us? And at a certain point, somebody said, well, there's probably 10,000 of them in the Milky Way. Well, there's not. Having a star like the sun with planets like ours is very unusual. It's very unusual. So anyway, this is the study of astronomy. And then down here, in this little bit smaller size range, we begin to talk about weather, and we begin to talk about geology. Things of that size are what contribute to our weather and to the large forms, landforms and water forms on the earth. Then we come down to the realm of life, ourselves and all of the animals, down to the fleas and down to the single cells. And then the realm of biology is closed. And we have the realm of chemistry and molecules, and then the realm of atoms made of protons and electrons. Now, what this means is that if you want to study physics, you're studying down here the protons and electrons. If you want to study biology, if you want to study chemistry, you're the next step up. Biology can only happen, life can only happen, when you have enough molecules to make a little pocket and put water inside that pocket and then do stuff. So life is never found in these tiny, tiny realms. Life requires this size range. And then when we move up to landforms, again, it's a specific size range that we're usually talking about. Of course, mountains are made of grains of sand, in a sense. At least grains of sand are what comes off a mountain when it erodes. But when we speak of mountains, we're speaking of a particular size range. If it's a lot smaller, we call it a hill, and if it's way smaller, we call it a tor or a boulder or a rock or a pebble or a sand grain. But the basic study of geology is here, and the basic study of meteorology is a little bit larger range, because in order to understand weather, we have to go up 6 miles so that we can look at all of the clouds and atmosphere, and then we have to go all the way around the Earth. So it's that size range. And then astronomy and cosmology. So really, this is a layout not only of the basic things that are in the universe, but of the basic disciplines of the natural sciences laid out according to size. There's something else interesting about this layout. These massive objects are governed by gravity. Gravity is a huge factor in them. Gravity is what makes them do what they do. Gravity is what causes the stars to burn. Gravity is what causes it causes galaxies to orbit each other, it causes stars to go around each other, it causes planets to go around stars. That's really what's happening. It's all about gravity. Even when you come down into the realm of life, our big animals are so governed by gravity that they're limited in what they can do. An elephant, it's huge, but it's so heavy that it has to have these enormous legs. If you try to make something twice as big as an elephant, then the legs have to be 4 times as big around, and then they don't fit under the animal anymore. So you take the animal out into the water. That's really what it comes to. So we go down here through the realm of biology, and when we come down into the realm of chemistry, we're in the realm of things which are interacting electromagnetically. That's what causes the atoms to interact with each other and to bond with each other. It's all electromagnetism. And everything down here does exactly what electromagnetism says, period. Things down here are not really all that affected by gravity. I mean, think even a baby spider spins his own little web and floats on the wind with it. He isn't really thinking about gravity. If you think about a giraffe, he's dealing with gravity every moment because he's got to pump his blood 15 feet up into the air in order to live. So these guys are all governed by electromagnetism. These guys are all governed entirely by gravity. If in this universe you wanted to have a free will creature, a creature who could make his decisions from within himself and not just based on physical forces, there's only one place. It would have to be some place big enough so that electromagnetism doesn't eat everything up, and small enough so that gravity doesn't eat everything up. And that's why we're where we are. And it's very interesting. Not only are we exactly the right size, we couldn't even be bigger in another part of the universe. Because just think about it. If we were bigger, even when we're bigger now on Earth, and we have a small number of people who are 7 feet, they have back problems, they have foot problems. If you would put them on a smaller planet so they could be lighter, that would seem to fix the problem, but the problem is that a smaller planet wouldn't be able to hold in the atmosphere that we breathe. So we can't have a smaller planet. We have to have a planet this size, and if it's very much bigger, then we start having people being scrunched down so much by gravity that we can't live. So anywhere in the universe, if there were other intelligent life, guess what? It probably would be your size and look a lot like you. So that's my introduction to the universe. Do you have any questions?
I thought the universe was infinite.
Well, here's the problem with an infinite universe. If you have an infinite universe, then you have an infinite amount of gravity. And if you have an infinite amount of gravity, then you don't have a universe. It just squashes together. There was a very long period of time when people thought that the universe was infinite. It's not really clear why they thought it. It seems to have been sort of a philosophical conclusion by people who just couldn't imagine it having a start. But immediately when people began to say that the universe was infinite, other people said, wait a second. It was called Olber's paradox. If the universe is infinite, the gravity is infinite, and everything gets squashed. Or, if the universe is infinite, with an infinite number of stars, all of them shining, then you would never have a dark sky, because there would be an infinite amount of light shining on every point. If you have an infinite number of stars, then you have an infinite amount of light. Now, the last effort that we have, and it's still going strong, to somehow escape from the impossibility of having infinite gravity and infinite light, is to try and spread out the universe so thinly and so far away that over there the galaxies are being pulled by the gravity on the other side of them, and so they're being pulled away from us faster than we pull them in, and so the gravity's not infinite here. Very clever. The problem with that is that in an infinite universe, in an infinite amount of time, sooner or later, these galaxies that are bumping around, a few of them are going to clump together and overtip their gravity. And then they're going to start sweeping up the rest of the universe into a great black hole of nothing. So it seems nice to talk about infinity, but really it doesn't work. For material things, you can't have an infinite number. So, another question?
Was there a beginning?
Well, see, that's one of the other things that's funny. If you have a universe infinite in time, can you do that? And it appears that the universe has actually a history. In the early 20th century, when Einstein was working out his equations for how everything works, he saw that his equations pointed to a beginning, because we have something called entropy, and entropy is not an increase in the matter, not an increase in the energy, but a decrease in the orderliness of the energy. Now, when you want to do work, there are really two things that you need. You need energy, but you also need an intellect behind that energy saying, go this way, go that way. When you think of a little child having a tantrum, there's plenty of energy, but it doesn't put things in order. In order to have things happen that have information in them, that have intelligence in them, that have direction, that cause beauty, you need to have order. And entropy is a continuous loss of the orderliness that's necessary for doing something interesting, for doing something that carries information. That loss of entropy is what demands that the universe have a beginning. And that demand is what finally made people say, okay, if there is a beginning, then the way that the stars are moving apart from each other, you should be able to say, well, they're moving apart like this, and we could, if we pulled them all back together, how long would that take? And figuring that out took a while. We're now thinking that it's between 12 and 14 billion years. It's not a huge amount of time. But that is the age of the universe. It's very uncomfortable for people who don't want to think about there being a personal God, or really if there's an intelligence in the universe, it would have to be also a person. In any case, the universe has a history. And actually the first person to say this was a contemporary of Einstein. And he said, Einstein, you have these equations which point to an age for the universe. And you have this little fudge factor that you're stuck in here called the cosmic constant. That makes it look as if your equations don't point there. And Einstein said, well, obviously the universe is infinite. And Lemaitre said, it's not obvious. What's obvious is that you have a fudge factor, and if you take it out, the universe has an age. Well, Einstein wouldn't, and Lemaitre wrote a paper called The Day Without a Yesterday, in which he said that the universe must have had a beginning, and we should be able to calculate it. And for a long time, people made fun of him. The phrase Big Bang was originally a phrase mocking Lemaitre for thinking that there had been an original explosion. But finally, somebody named George Gamow said, well, if Lemaitre is right, then that original explosion would have sent radiation out into the universe, and that radiation would still be moving out into the universe. And we can't see it now because we can calculate what the wavelength would be, and the wavelength is something that we don't know very much about right now in the 40s. But he said our instruments will improve, which they did. And in the 60s, when we began to work with microwaves, somebody finally found Penzias and Wilson. And Lemaitre was an old man. He was on his deathbed when the news came that this cosmic background radiation had been found. And so he died happy. And you, if you step outside at any time of day, but especially at night, and you hold out your hand, the radiation from that first explosion falls directly on your hand right now. You're a child of the everlasting Father, and the light of that first moment of creation is still falling onto your own hands.